In this video, I'm going to show you the formulas for friction and some of the rationale behind how we calculate the force of friction. Okay, so this is the definition. It is that the force of friction is the force you need to drag one object across another. Of course, at a constant velocity, because if you are accelerating the object, then of course the force would be the force of friction plus the force needed to accelerate the object. Okay, so if you think about a box sitting on a surface here, gravity is going to pull down. That's what this little mg is here, right? The surface is going to push up on the box. We might apply a force this way, and the force of friction, if the box is sliding that way, would act to the left, okay? We think it depends on how hard the surfaces are held together. This is almost always, by the way, the weight. It's almost always just m times g. Unless you're on an inclined plane, or unless somebody's like exerting a force upward at an angle, and then it might be less than mg. And if we're pushing down on it, then it might be more than mg. Okay, but usually it's just the weight of the object. And then it also depends on what type of surface it is. Is it rough? Is it smooth? We'll get into that in just a sec here. We think it shouldn't depend on, it's not supposed to depend on the surface area. So the rationale here is that if we've got like a rectangular block of wood, if we put it on a large area toward the ground, the pressure is less. And if we put it on one of the smaller sides, the pressure is more, but there's less area. Okay, so that's roughly true. And it's also not supposed to depend on the speed that you're going. And this is true if you're going at low speeds. Obviously, as soon as you get air friction into the picture, it'll vary with speed tremendously. Okay, this is the formula. That guy there is the force of friction. This is the coefficient of friction. That's the Greek letter mu. Mu. Okay, and it's a number, pure number between 0 and 1. And then this is the normal force. And usually that's equal to the weight of the object, right? Okay, so if gravity is pushing down, the surface will push up with a force equal but opposite. Okay, so that's the formula. And I'll get into some more specifics about the formula. This would actually be for kinetic friction. It turns out there's two types. Let's look at some of these coefficients of friction. This is a table of coefficients of friction. Now, please don't write these down and memorize them or anything. You would look these up. These would be given to you. I'm just showing them to you here so you get some idea of what we're talking about here. Notice that rubber on dry concrete is quite grippy. Rubber on like a gymnasium floor can be quite a lot. You can get coefficients even bigger than 1, which is kind of amazing if you're not moving. Okay, so there's two different columns here. Static is stationary. Kinetic is moving friction. So if it's already sliding, this is the column you use. If it isn't sliding yet, this is the column you use. And this, of course, these giant coefficients are why you can injure your ankle if you're playing basketball, because you've got so much friction there. Notice that things that are really slippery have small coefficients, and things that are grippy have large coefficients. Okay? This is some definitions, and you could write this stuff down if you want to. The kinetic friction is the force to keep it sliding at a constant velocity. Okay, there's the formula. Notice that there's an equal sign in that formula. Okay, it always opposes the velocity. So if you've got a block and the block is sliding that way, the force of friction will be opposite that, right? Static friction is the force needed to start something moving. Okay, it is. Notice that this one is expressed as a limit. The force of friction is smaller than or equal to whatever that is. Okay, so it keeps the object from moving if it can. It's only relevant if the object's stationary, if it's not moving. It always opposes the applied force, right? Okay, and the calculated value is a maximum. So let me just give you an example here. If we've got a box, and let's suppose that we figure out, we go the normal force times, static force times m times g in this case, right? Let's suppose that equals 17 newtons, just for fun, right? That's as big as static friction can get. If I exert 5 newtons this way, and it's sitting still, it laughs at me. It goes, you can't move, so it exerts 5 newtons this way. If I exert 6 newtons this way, it exerts 6 newtons that way. If I exert 12 newtons to the right, it exerts 12 newtons to the left. If I exert 16 newtons to the right, it exerts 16 to the left because it keeps the object from moving, right? So But if I exert 17.0001 newtons to the right, little bonds, little molecular bonds that have formed there break and the object starts to move. Okay, so it's like a betting limit. It can only bet up to that amount. It sees anything you do. If you say 5 newtons, it says, I see your 5 newtons. If you say 12 newtons this way, I see your 12 newtons that way, right? So that's the maximum that it can get. It's only to answer the question, will it move? It's never used to calculate an acceleration of an object. It always happens before the object starts to move, okay? That's pretty much all you need to know about friction. I would look at the examples in the next part here. I'm just going to bust out some examples.